we have any kind of timeline on the first test?
My hope is for it to be, hold on, I'm actually going to show it because the last week of February is also the first week of March, and that's when I want it.
Gotcha, all right.
That's the week before midterm grades go out.
Right.
Good day all. To say what I just said more louder, I've been asked when the first test is. My goal is for it to be the week of the 27th through the 3rd. So that's last week of February, first week of March. The reason for that being that's the week before midterm grades go out. And midterm grades specifically go out on March 10th. And I like giving the test during lab period so that you can have as much time as you need, not have to rush in after one class and rush out to another. So the idea would be during lab that week, rather than show up to do a lab, you would show up to here and to take your test. And it would be that week because there are people who take lab on Friday and midterms go out Friday morning, so that's not that timeline doesn't work out. I may play around with it a little bit more in case we just need a little bit more time. Like I might sacrifice lab on 2 weeks to start it on the 3rd and run it through the 8th. I'll figure that out as we go, but it'll be in that ballpark. And it will be during lab time, so you have as much time as you need to take it, and we will spend time prepping for it beforehand, and I will make sure that you have a list of concepts to study and a list of practice questions, a full practice test that you can do. The issue getting there right now is just chapter 2 is really long. I never remember how long it is until I'm in the course teaching it every year. There's just a lot of things contained within what the textbook that the course is based on calls chapter 2 before we then move on to 3 and 4 and then the test. So I may do a little bit of restructuring on what is arbitrarily labeled chapter 2. I might switch a few homework questions between different assignments, like move momentum out of 2 and into 3, because 3 is supposed to be about momentum. So if you see the homeworks and quizzes changing in the coming days, it's in that I'm trying to make them easier and consolidate all the momentum stuff together in one place, rather than it being split between 2 and 3.
So we're looking at somewhere in between the 27th through the 10th.
Correct. It'll be in that ballpark so that you take the test and the grades will be factored into the midterm score that you see. Now, as a reminder, at this school, midterm, at least in it, sorry, rewind. For this class, there is no technical midterm assignment. There's just the first test that is factored into the score you see on midterm day. Does that make sense? I much prefer having the test one before that midterm, because if it comes after, then the midterm's kind of pointless. So that's what I'm currently scheduling around. It'll be in the days before the 10th. I may have to sacrifice 2 weeks of labs for it, but I'm comfortable doing that. We've been going at a pretty good clip as far as labs go. Yeah, that's sounding more like a feasible idea. The more I say it out loud. All right. I addressed concerns about that one for the time being. Okay. As we get closer to it, we will spend time in class going over things, and I will make sure that you know beforehand which days are the test days. But it will be during lab between the 27th and the 8th. Lab days between those times will be test season. Now, for the short term, the stuff we're doing right now, my goal, after a little bit of restructuring, is we're going to finish up chapter 2 this week. Today we're going to be going over another form of energy and talking about how work transforms energy between the various types. We'll close out chapter 2 on Friday with a discussion of power, the idea of energy being used over time, and that's when I'm going to officially call chapter 2 done. And we'll move all the momentum stuff to chapter 3 next week. for right now, as we begin, before we dive back into work and energy and force, any other questions, comments, etc. at this time about anything at all? All right. In that case, what slide was I on? Bless you. Bless you again. Bless you also. All right, so last couple days, we've been discussing the physics concept of work, the idea that when you exert a force on something and cause it to move, you are using up energy in your own body and giving it to whatever you've done work upon. Because if you push something to the side, you want it to move to the side, and so you use up the energy in your muscles to give the energy to the box and to make it start moving. Because everything needs energy to be able to do stuff. Energy is just this invisible thing that matter possesses that allows it to act. So for the box to move, it needs energy. You do work on it and push it to transfer energy out of your own muscles and into the box to get it to move. So the process of doing work is the notion of using, transferring, and transforming energy between various objects and between various states. When you do work, you are using, transferring, or transforming energy. And typically speaking, you are going to transform the chemical energy in your muscles into kinetic energy into a separate object. Because if you want something to move, you have to give it kinetic energy to make it move. To that end, we defined and put a formula on the concept of kinetic energy. If you see something moving, that object possesses kinetic energy. It's the form of energy that allows matter to move. Formula is 1/2 times mass times velocity squared. This says that the faster you want something to go, the more kinetic energy it needs. Hence why your car has to burn more gas to go more fast. Questions before we pick up from here? All right. Now, as I said, it takes work to give things energy. That includes kinetic energy. So, we'll start off with a review example to compare these related phenomena to a particular force that some of you may or may not exert on a regular basis, baseball. You can substitute your particular sport of choice here, because all of them involve forces and all of them involve throwing or punching or kicking something some distance. For this case though, for simplicity's sake, we have a 100-gram baseball and we're going to throw it. As you throw, you exert a 10-Newton force on the ball for a distance of 1.2 meters before letting it go. Pictures are always helpful, so let's draw one. Here we have our baseball. We're going to exert a 10-Newton force upon it, and it is going to move 1.2 meters while that force is being exerted, while the ball is in contact with our hand. What this looks like in real-world terms, again, whenever you throw anything, you typically hold it in one or more hands, you wind up, and then you start exerting the relevant force on it. So at this point, I'm now going to begin the 10-Newton force. And as I exert that force from the wind up, it now moves a distance forward in my hand while that force is still acting on it. So this entire distance, that 10 newtons is acting from here to here over the entire wind up. And then at a certain point at the end of my arm length, I let it go. Ooh, I will never repeat that feat. That was amazing.
Could do that again if you tried.
I can't even hit the trash can, let alone aim styrofoam into the sink. So, force is applied over a distance of motion. This is true for throwing, it is true for punching, it is true for hitting something with a ball or a bat or a racket, it is true for kicking. And I mentioned in the past that I took Taekwondo as a kid. My Taekwondo instructor is the one who taught me F equals MA. Similarly, he taught me about this because in my style of Taekwondo, one of the strongest kicks you can do is a side kick, which involves winding up your leg like this, and the leg moves a distance out as you exert force the entire time. So distance, force applied, and then you reset for another kick. So all those various activities, force is exerted as the ball, your hand, your foot, your bat moves some distance. Got our picture. We'll rewrite all of our variables over here. The ball has a mass of 100 grams. The force applied is going to be 10 newtons. And our displacement is going to be 1.2 meters. So, after all that, first question, how much work do you do on the ball?
So work equals force times distance.
Precisely. You've got force and distance, you want work. Work equals force times displacement, distance. The caveat being that the two have to be parallel to each other, and that is the case here. We're going to exert a, from your perspective, rightward pointing force, and the ball is going to move to the right as it's in my hand. So the parallel rule matches here, so we can multiply our force times our displacement. And that should give us, bless you, a work accomplished of approximately 12 joules. That means throwing this baseball in this manner takes 12 joules of energy from your own arm. That is 12 less joules, like you have 12 less joules after you do this. That is the energy cost of this particular action. And since every single toss has a certain energy requirement, if you do this repeatedly, you tire your arm out because it runs out of energy. So, questions arriving at this number? All right. Now, next question, related to this number. This is the amount of effort it took to throw the ball, the energy it takes to perform this action. How much kinetic energy is the ball going to gain in this interaction? Bless you.
Would we have to find velocity?
Not quite. We will get there. We are going to eventually arrive at velocity. But we can actually estimate how much kinetic energy the ball gains before that. The reason being, due to a principle that we're going to define today called the law of conservation of energy. Does the idea of energy conservation sound familiar? Okay. Well, does the idea of matter conservation sound familiar? Matter cannot be created or destroyed. All right. Turns out energy works the same way. If you have a certain amount of energy in a system, you can't destroy it. It just transfers which object has it and what form it's in. If energy exists, it will continue to exist. It's just going to go somewhere else, possibly into a form you can't really measure. In this particular case, when you do 12 joules of work throwing something, you now no longer have that energy in your arm. You spent it to perform the action. But that 12 joules doesn't vanish. It's not gone. It has to go somewhere. It has to turn into another form. That 12 joules initial has to become 12 joules final somewhere else. And the entire purpose of throwing is to take that missing energy and send it into the object you're throwing. So if we lose 12 joules of energy doing this, the ball is going to gain 12 joules of energy. And if the purpose of throwing is to make something move, what form do you think that energy is going to be in?
Kinetic.
Kinetic. Exactly. It's not a trick, I promise. You throw something, you do work to give kinetic energy to the object you're throwing so that it starts moving. So, following along from the idea of conservation of energy, we had 12 joules of energy to begin with. It has to go somewhere, and it's going to turn into the kinetic energy of the ball. By doing work, we have transferred energy from your own muscles into the ball, and we've transformed it from chemical potential into kinetic. Again, the purpose of work is to use, transfer, and transform energy. And in doing this, we've done all three. Feel all right so far? All right. So, we use up 12 joules. In an ideal system, the ball's going to gain all 12 of them in the kinetic state. So that answers that middle question right here. In an ideal system, the energy you use up ends up in the object you did the work on. Last question then. How fast are we going to throw this ball?
Well, now that we know kinetic energy, we know the mass, we can find the velocity, right?
Yes, we can. You recall the formula for kinetic energy? My marker's starting to get the high on me. I apologize. Kinetic energy, in general, is 1/2 times mass times velocity squared. Can you guys read this? Getting very mixed reactions. That's fair. Just open this marker too. Better? All right. Kinetic energy is 1/2 times mass times velocity squared. The ball is going to gain kinetic energy because we threw it, and it's going to have a certain velocity because it has that energy. We know how much KE it gains. We know the ball's mass, so we can figure out how fast we threw it. So 12 is going to equal 1/2 times the ball's mass. Are we going to plug in 100? No. What are we going to plug in? Very good. How many kilograms is this?
0.1.
Fantastic. Thank you to everyone who said it, but if you said it very quietly, my ears aren't that great. I apologize. So we're going to plug in 0.1 instead of 100. All our formulas want kilograms. And now we're set to solve for velocity. The journey there, just to show algebra steps, I would divide by 1/2. That would give me 24 equals 0.1 times v squared. Divide by 0.1, that would be 240 equals v squared. Therefore, final velocity is going to be the square root of 240, which, if I remember correctly from the last time I did this one, is a little more, about half, yeah, I think it's about 15.5 meters per second. Does anyone's math disagree? Feel all right? Feel good? I hope. Please let me know if it doesn't. All right. Now, We analyze this through the lens of work, kinetic energy, and energy conservation. This is not actually the only way to do this question, because ultimately, secretly, you can figure out the speed the ball will move at using the first four formulas we talked about. Because you know the mass of the ball, you know the force you're exerting on it, you know its displacement. So you could, if you wanted to, use our original formulas instead. Namely, I'd say this one. In conjunction with Newton's second law. Now this marker's dying, fantastic. If you know the force on the ball and its mass, you can find its acceleration. We know its acceleration, we know how far it goes, we can figure out its change in velocity. So this method also works. So what we've done here is not a replacement to how we used to do things, it's an additional layer. It's a bunch of stuff that's going on at the same time. Because using again, our old formulas, we can still describe this as you're exerting a force on a mass that causes acceleration. Acceleration is going to change its velocity. That's all still true. That is the mechanism through which energy is exchanged. Force and work, force is the mechanism through which work is done, through which energy is exchanged. So all the old stuff connects and it goes along with all the new stuff. It's not a replacement, it's a supplement. So now you can describe it in terms of force, mass, acceleration, but also in terms of energy. And oftentimes you'll mix the approaches. Sound right so far? I know I ask that every 2 minutes.
Better than not enough.
That's fair. It's better than the opposite problem, you're right. I'd rather be annoying than not give you the information.
Agreed.
All right. Now, as discussed, when you do work, you use transform and transfer energy. And transforming energy means you can take it from any state and turn it into any other state. You can convert from kinetic to electrical. You can convert from nuclear into heat. You can turn any type of energy into any other type of energy through using work. And for that reason, we need to define at least one more form of energy so that we can convert energy back and forth between the two forms. Now, kinetic energy is, I'd say, the easiest type for humans to view with your eyes and conceptualize, because if you see something moving, you know it has energy to move. There's a certain conceptual understanding of that. And you've seen things moving your whole life. This next form of energy, it's a little harder to describe because it's basically fully invisible. It is the notion of gravitational potential energy. Next form of energy we want to talk about, and I'm going to describe it to you, but I'm going to need, it's okay if this one takes a second. Of the two forms of energy so far, this is the weirder one. I mentioned last time, you guys brought up the idea of potential energy, which was great. If energy is in a potential form, that means it's being stored up for use later. It's not actively in use at the moment. It's being stored up like in a battery. Batteries hold electrical potential energy. You plug something in, you plug a battery into something, you turn it on, and the potential gets used up. But you don't really see the potential while it's being stored. You can't look at a battery and with your eyes figure out how much juice it still has in it. Similarly, food is technically a form of potential energy. There's chemical potential in a loaf of bread. You eat the bread, and now there's chemical potential in your body that your muscles can turn into kinetic energy. So you can't see the potential while it's stored. You only really notice it once it is transformed into a more active state and you can observe it in use. That's still true here, because you can't really see GPE while it's being stored up. You only know it's there once it stops being GPE. But it's still important to define the GPE energy state. And the definition of GPE is that it is energy stored in an object's ability to fall. Batteries store electrical energy, the ability to create electric current. Food stores chemical potential energy, the ability to have the energy released and burned. GPE is energy stored in the ability to fall. Does that sound weird? That's allowed to sound weird. It's a weird principle if you never thought about it before. But I'm gonna do my best to make it make sense. When you lift something into the air, that process takes work, correct?
Yep.
Because according to the work formula, I'll use a Y instead of an X. To lift something, you exert a force and you cause it to move some distance upwards. So lifting anything takes work, correct? So in doing this task over and over again, I do work and I use up energy. There is energy burnt up that is now no longer in my muscles because I did this. Now, if that energy is not in my muscles anymore, where is it? It can't be destroyed.
In the object.
It is in the object, very good. You can't see it in use currently because it's not in use. The object's storing it for later in a potential state, specifically the gravitational potential state. Because what this marker is waiting to do, it's got all this energy on a hair trigger ready to go. What it's waiting to do and burn that energy for is that. It has energy stored so it can fall. Because if it didn't have any energy ready to go, it wouldn't do anything when I release it, right? If it didn't have any energy stored up, it just wouldn't act. But it does have energy stored, so it starts acting. It then starts converting that energy into a different state, namely kinetic. The act of falling takes stored GPE and turns it into kinetic energy on the way down, which is why it then gains a velocity and starts heading towards the ground. Because gravity can do work like how friction can. Friction takes kinetic energy and turns it into thermal energy. Gravity, work done by gravity, takes GPE and turns it into KE. Because it needs that stored up energy to then turn into KE on the way down. If it didn't have any stored up energy, there'd be no KE to turn into. It just would remain there. So the mechanism of gravity, the force of gravity, causes that acceleration and it turns the GPE that's stored into KE on the way down. This is, I'm explaining this with the goal of using it as verification that there is energy stored in the marker that is released upon dropping it. And as an additional example, try to help make the point. You guys know what a water wheel is, right? Mine's gonna look like the sun, so my art is all stick figures. For a water wheel to work, you need running water to move under or over it. And a pretty common way of doing that is to park your water wheel next to a waterfall. Water falls off the fall, falls onto the wheel spins, and then you can turn on the lights. When the water's up here, it has stored GPE. And once it starts falling, that stored GPE is released. The water wheel absorbs some of that energy, turns it into electricity. So the very fact that this is able to power your light bulbs or what have you is proof that it gained energy from the water that it had up here. The water had energy up here that eventually ends up in your light bulb. So again, the goal being proof that there is energy up here. You just can't see it until it starts falling, until it does something with it. Sound okay so far? Any objections, queries, haiku? All right. So, the actual formula for GPE. The variable is just abbreviated to GPE. You can see it on your formula sheet. It's like KE, it's just gonna be multiple letters because I don't have a better abbreviation for it. GPE, it's a form of energy, so we're still gonna measure it in joules. Every form of energy is gonna be joules for this class. The GPE that an object currently possesses is equal to its mass times G, which is gonna be 9.8. It's the magnitude of gravity on this planet, times its current height from your perspective. Now if I was to translate this formula into more meaning, like to extrapolate meaning from it, this means the more mass an object has, the more work you have to do to lift it into the air, correct? It takes more work, more effort to lift this than it does this. If it takes me more effort to do that, that means I have to spend more work to do that. I lose more energy in that action. And that means that the heavier object gains more energy. Because it has more mass, if I lift it up to the same height, it's stored more GPE in itself. Which means if I was to drop it, I'm not actually, if I was to drop it, it would bring more energy, it would release more energy into that fall, and it would hit the ground with a bigger boom. Because it had more energy, it brought more energy into that crash. Because it had more energy to release upon falling. That's why you don't want to stand under a falling anvil, among other reasons. Very heavy, brings a lot of energy. So, more mass something has, the more work it takes to lift, the more energy it stores before it falls. It's also conveniently why it's very easy to lift very light objects. It does not take much work, they store very little GPE. The next term is G itself. Again, magnitude of gravity. This depends on what planet you're on, because it's harder to lift things on Jupiter than it is here, for a myriad of reasons. Meanwhile, it's easier to lift things on the moon because G is smaller there. There's one thing to note, though. I've been very insistent that G is negative 9.8 for this entire class. This is one of those formulas that you actually don't want to use that negative sign, though. Namely because this formula is about the energy you gain when you lift something upwards, bless you. And plugging in a negative number suddenly breaks the formula, because if you use that negative there and nothing else canceled it, you'd suddenly have negative GPE when you lifted something. It doesn't make a whole lot of sense. So I've got two ways to describe this paradox. One, mg, if you were to couple these two letters together, think of them as one unit, that would represent the amount of force upward you need to exert to lift something. The weight would be m times negative 9.8 downwards, but the opposite of that, the force needed to lift an object, would be the positive version of that number, hence why the negative disappears. Now, that's kind of hard to summarize on your formula sheet. So instead, I recommend writing absolute value brackets. Just to make sure you don't put that negative in there. That's the second way of thinking about it. So that's just what gravity has to do with it. That's the strength with which gravity pulls something down, the rate at which it falls, the rate at which its GPE turns into KE on the way down. Last term is H, which just means that the higher you lift something, the more effort it took to get it there, the more energy it stores, the further it can fall. H is a little bit relative though, because if I hold this 2 kilogram weight above the desk, if it falls to the desk, it's going to release this much energy. But if I step backwards and it falls to the floor, it's going to unleash more energy. And hypothetically, if I let it fall to Earth's core, if I had a hole that deep, it would unleash even more energy as it eventually lands in the core and melts. So H is kind of relative. It depends on the type of question you're setting up. It depends on your frame of reference. But I'll make sure that the frame of reference is always clear on a question-to-question basis. Usually it'll be compared to the lowest point listed in a problem. But again, I'm going to try to make it easy. So, those are the three things that affect how much GPE an object possesses. And that GPE is released once you let it go and allow it to fall. Objections, questions thus far? All right. Got a couple quick questions I want to look at in relation to this. First, kind of the same thing we did for KE. Which of these two scenarios has more GPE in it? We have a 5,000 gram object that is lifted a height of 10 meters compared to a 100 kilogram, object that has been lifted by 10 centimeters. Which case do you think has more GPE in it? Bless you.
That's it.
All right. Any other bets? Anyone bet against A?
Going B,
All right.
just because you went A. I mean, yeah.
So just to play the contrarian then?
Yep.
All right. So, we take the masses, we take the heights, we plug them into our formula. The thing to keep in mind here is units. Because the first question gave you grams instead of kilograms. All our formulas want kilograms. How many kilograms is this? Is 5,000 grams. Very good. Pop a decimal point there. 10 meters is fine, so that's going to give us a GPE of 490. Down here, we were given kilograms for mass, which is great. We were given centimeters for height. We want meters for that, so how many meters is 10 centimeters? 0.1. So that's going to give us a grand total of 98 joules.
Man, got me though.
So watch your units. Just make sure to double check them whenever you do any math in here, really. This formula, nothing is squared, unlike the KE one, so it's not like one variable is more important than the other, but that means it's all the more important to make sure you check all of your units. For comparison's sake, this is the energy drain of lifting, a decent-sized moving box up about 3 stories. This is the energy it would take a human of roughly my shape and size to climb up 1 stair. Now, that said, if you, a human, are carrying a box upstairs, you are actually draining both of these at the same time, because you do this every time you raise up 1 step, in addition to this, by dragging the box up that number of steps. So, whether you have a box in your hands or not, climbing steps is actually surprisingly taxing. Questions thus far? All right. One more thing I want to look at briefly, and before I put any numbers in front of you, I want to make sure that you have this in your notes. I mentioned this a second ago, law of conservation of energy. It's the notion that energy is not created or destroyed. If a certain amount of energy exists in a system, that total value doesn't drop. It can just be distributed among different forms and exist inside of different objects. A good example would be driving your car along and you take your foot off the gas. Cruise control is not on, car starts slowing down because of friction. Friction does work on the car, it takes energy away from the car. If the car had 1,000 joules of kinetic energy going forwards and then it stops, does that 1,000 joules of energy cease to exist? No, friction just turned it into heat. And that heat is now distributed between your engine and the earth. So, isn't destroyed, it just goes somewhere else in a form that may be harder to see, but it's still there. This part just says energy initial equals energy final. Whatever the total is will remain true. So, to quickly summarize that into one more example, we're going to put some numbers to dropping a heavy object. Wrecking balls, pretty heavy, one of the more routinely heavy things someone could attach to a crane. wrecking ball is going to have a mass of 2,500 kilograms, which is more than most cars. Or equivalent to an SUV, perhaps, at least a large sedan. And this wrecking ball is attached to a crane that has lifted it up to 15 meters in the air. That takes a lot of work. It takes a lot of effort to lift an object like this. Just hands down, no question about it. So, first question, how do we find the GPE that this wrecking ball will have as it sits right there in that position?
Just multiply everything.
Yep. GPE formula, MGH, namely the absolute value of G. I want to make that clear. So we take our mass, which is already in kilograms, a very large amount of kilograms. 9.8 times height of 15. And this is going to give us a real big number. If memory serves. $367,500 joules. I'm not entirely sure about this next point, but that may be more energy than you eat and use in a day. Which is just to say, a human's not doing this unassisted. So, that is the GPE that it has sitting at that height. It's just attached to a crane, it's just being held there. And in that position, it has this much GPE. That means the crane had to use this much work, use up this much energy to get it there, if it started on the ground. So that's a lot of gas. Demolitions work is very expensive. So, next question. When this wrecking ball is eventually released, let's say someone's parked a car to be crushed down here, and we're going to just release it and let it fall. What's going to happen? Sorry, rewind. How much kinetic energy is the wrecking ball going to have at the last possible second? This is the moment where height is 0, but we've kind of freeze framed right before the crash actually starts. So, no boom yet, freeze framed right on, top speed, height of 0. In that moment, how much kinetic energy would the wrecking ball have?
367,500 joules.
367,500. And we know this because law of conservation of energy tells us energy initial must equal energy final. If the wrecking ball has this much energy, it will continue to have it, even if it transforms into a different type. Now up here, if the wrecking ball is just being held in place, all of its energy is in the GPE form. Once it's released and it begins falling, what happens to this number? Well, it decreases. You're absolutely correct. This number is going to get smaller as the wrecking ball descends because its height is going to get smaller as the wrecking ball descends. So every moment it spends falling, it loses GPE. But that energy isn't just gone, it turns into KE because of the work that gravity is doing. Gravity transforms GPE into KE. So as GPE drops, KE rises until at that last moment at the very bottom, they've completely swapped. the top, you are stationary and have as much GPE as you're ever going to have. At the bottom, you are zooming, you got as much KE as you can possibly have and no GPE left. So it's an exact one-to-one conversion of one to the other as you fall. So, that law of conservation just tells us, however much energy we have to keep it all the way through. And if we don't have any GPE left at the end, but we are moving, it means all of it had to turn into the KE state. Gravity did work to transform it. Wrecking ball still has it, it's just a different type. So, the wrecking ball will, at that very last second, at the lowest, last possible point, have 367,500 joules of kinetic energy. This is why lifting a heavy thing in the air and dropping it crushes things. The heavy thing brings a lot of kinetic energy into the crash because it had a lot of GPE to turn into KE. And since it's bringing a lot of energy into the crash, it's going to be moving very fast, it's going to exert a very large amount of force, and whatever's under it will become a pancake and then part of the subsequent crater. So, any questions or issues arriving at this conclusion? All right, last question. What will the wrecking ball's velocity be the moment right before it strikes the ground? Again, the moment it's at top speed before it actually goes boom.
Would you use the kinetic energy formula?
We can, in fact. Whoops. We'll start at 0 instead of a 5. So instead of KEF, I'm going to write in the kinetic energy formula. 1/2 times the mass of the wrecking ball times our unknown final velocity squared. And much like before, we can solve for the velocity, divide by 1/2, divide by 2,500, and that should, again, if memory serves, give a final velocity of about 17 point something, 17.16?
17.50.
17.15 meters per second. Which again, pretty quick, and will make a very large crash. Now once again, this is happening concurrently with the old formulas we would use, the old fantastic four equations, which say, you know, as you descend, gravity is causing an acceleration, will change velocity from 0 to 17.15. That math still works. And technically, it means that any object dropped from that height would be moving at 17.15 before it hits the ground. But the wrecking ball brings more kinetic energy into the crash, so it's going to exert more force upon hitting the ground. Like dropping a marble from the same height, it would hit the ground at the same speed, but the marble brings less energy, therefore it's not going to do nearly as much damage as the wrecking ball does. Bless you. How do we feel so far? Okay. On Friday, we're going to talk about one more energy-related concept for now, tie everything together, close out Chapter 2, and then next week, we'll begin talking about momentum in Chapter 3. Questions, objections, concerns? All right. Have an excellent day. I'll see some of you for lab. I already said